Alright guys, here we're going to talk about electrophilic aromatic substitution, and in particular what happens when you put an electron donating group on the ring. We've already discussed in class that electron donating groups activate the ring, making them react faster than benzene. That's because the more nucleophilic you make the ring, the faster it's going to react. What we're really going to focus on now is the regiochemistry of the reaction. What happens when there's an electron donating group on the ring? And hopefully you've read that electron donating groups typically direct orthopara. I want to make it really clear that I'm not talking about halogens right now. Halogens are in the class all by themselves, and we'll discuss them later. I'm talking about other electron donating groups. So I'm going to show you what happens here with phenol. Phenol is a benzene ring with an alcohol group, and an alcohol group is very electron donating because the lone pair of electrons can go into the ring based on resonance. So first what we're going to do is we're going to see what happens when the electrophile goes to the ortho position. And I'm just using a generic electrophile E+ here. Remember, it can be any of those super electrophiles we learned about previously. NO2+ for nitration, carbocation for Friedel-Crafts alkylation, an aselenium ion from Friedel-Crafts acylation, so on and so forth. So what we're going to do is we're going to put the substituent in the ortho position first. In order for that to happen, this double bond is the one that's going to react because that is the ortho position. So the mechanism is that the nucleophile attacks the electrophile goes to the ortho position, and there's still that hydrogen there that was there in the begin with. So the electrophile went to one side of the double bond, the carbocation goes to the other side of the double bond. These stay intact. Now let's draw the resonance structures for this, and this is where it gets really crucial that you can draw resonance structures. One resonance structure has that double bond moving over, so we form this structure here, and the carbocation is at that particular location. And there's one more where this double bond comes down, and you form the carbocation at this position. So those are the three resonance structures if the substituent goes to the ortho position. And I'll come back and talk about that in a little bit. Now let's see what happens if the electrophile goes to the meta position. So this is the meta position. So we're going to take that same double bond, react it with the electrophile. So the electrophile goes to the meta position, and it still has a hydrogen there. These double bonds remained untouched, and the electrophile goes to one side of the reacting double bond, the carbocation goes to the other. Now let's draw the resonance structures again. So one resonance structure is if that double bond moves over and you form this carbocation. And then the last resonance structure looks like that. Okay, there we go. All right, so those are the three possible resonance structures for if it went into the meta position. And again, I'll talk about them in a minute. Last but not least, let's see what happens when the electrophile goes to the para position. We're going to use now this double bond to go into the para position. So the double bond reacts nucleophilically with the electrophile. You're left with these double bonds untouched. The electrophile goes to the left-hand carbon here. The carbocation goes to the right-hand carbon there. So that's one of our resonance structures. Let's draw some more. So one possible resonance structure then looks like this. And then the last resonance structure, oops, it was supposed to be black, there we go, looks like this. So you can have 9 possible resonance structures. It's not particularly hard to figure them out, it's just a bit tedious. Now, let's analyze this to figure out what resonance structure or structures is the most stable. Whatever resonance structure is the most stable will be what dictates what the product is. So here, if we look at our 3 resonance structures for the ortho position, This resonance structure is very stable because we can take a lone pair of electrons, donate it into where that carbocation is, and have one more resonance structure available to it. It's not a particularly stable resonance structure because you have the positive charge on an oxygen, but it still exists. So the ortho position is favored when you have an electron donating group on the ring already, because this resonance structure allows for the most stable resonance structure. If we look at the meta-substituents, they're all kind of the same. You have the positive charge on what looks like a secondary carbon, nothing particularly stable, nothing particularly unstable. Let's look down now at the para position. We have this resonance structure. If you look at it, it should look very similar to what we just did for the ortho structure. You have the carbon, the positive charge right next to the electron donating group. Because it is right next to the electron donating group, you can get electron density to come in and stabilize that carbocation. So let me just finish drawing it out here. Because the ortho and para lead to an extra resonance structure, electron donating groups, direct ortho-para, the regiochemistry will have the electrophile be ortho to the substituent on the ring, or it will have the electrophile being para to the substituent on the ring.